Bismillahirrahmanirrahim. Inshallah, today we will start chapter 2 in Algebra 2. This chapter is about polynomial functions. We have seen some of these before actually, but we are going to elaborate on polynomial functions in this chapter. Now, you already know what a polynomial function is. We've described this before. Here's an example: 7x to the fifth minus 4x cubed minus 3x squared minus x plus 5. That's a polynomial function of fifth degree. We talked about this before. And these are the coefficient of the variables. This is 1 here, and that's the constant term. And we even said this is called the leading coefficient. That's the leading coefficient. So this is an example of a polynomial function. Now, if you understand this, then look, a function like this, f of x is equal to 5. This is y is equal to 5. This is a horizontal line. This is technically, a polynomial, right? Polynomial of 0 degrees, so to speak, right? And then f of x is equal to, I don't know, like 5x minus 5. This is a line, y equals mx plus b. So this is a linear function, but it's technically also a polynomial function. Okay, so this is a constant function, this is a linear function. And the last chapter was all about specific polynomial functions, and that was like this type of a function, right? It was like x squared plus 5x plus 6. So this was a quadratic functions, right? So that's a quadratic function. But these are technically polynomial functions too. But when we're talking about polynomial functions here, obviously we're talking about the broader category of polynomial functions, like these type of polynomial functions, because these we have talked about individually before. So in this chapter we're going to talk about polynomial functions as a broad category, broader than the quadratic functions that we have seen before. So a quadratic function, by the way, as we have said before, is a second degree polynomial function, and this is a quadratic, and then a third degree polynomial function is a cubic function, and if you're curious, also a fourth degree is a quartic, Q-U-A-R-T-I-C, a quartic function. So again, these are all polynomial functions, but now we're going to talk about polynomial functions here in a broader category. So first thing we have to do is the example I gave, for example, 7x to the fifth minus 4x to the fourth plus 2x cubed minus x squared plus x minus 3, for example. This is a polynomial function of fifth degree, and in all good manners we arrange the degrees from in descending order. And the leading coefficient was 7 and the constant term was 3. Okay, now for a linear function we had y equals mx plus b, and for a quadratic function we had y equals ax squared plus bx plus c. These are like the generic polynomial functions. Now we have to be able to do this also. We have to be able to write a generic polynomial function, right? For example, this polynomial function, you could say generic for all fifth degree polynomial function could be something like, okay, a to the fifth of x to the fifth plus a to the fourth x to the fourth plus a to the third to the x to the third plus a second of x to the second plus a first x to the first plus a 0 x to 0. Now this could be a generic polynomial function. Now, here, a to the fifth, right here, a fifth means, this means the coefficient belonging to the fifth degree. This is not like a to the power of 5 or a times 5, whatever. It's just a subscript saying the coefficient of the fifth term, because you're going to run out of alphabets pretty soon if you start using a. But what if you have a polynomial that's like 36th degree, you know? You're going to run out of alphabets, so you have to use this subscript. So a subscript 4 means the coefficient of the fourth degree term. A subscript 3, A3 is a coefficient of the third degree term. A subscript 2 means the coefficient of the second degree term, etc. until you get A0, which is x to the 0 technically, right? But is the coefficient of this, and this is the constant term. So this is a generic for fifth degree of polynomial functions. But polynomial function, as you realize, can be, infinitely long, right? You have, what if they have f of x equals, a negative 5x to the 215th plus 4x to the 214th plus da 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 da, right? It could be extremely long, right? So we have to be able to write a polynomial function in a generic way. How do we do that? Okay, well, this is how we do it. So here's how you write a generic polynomial function. So f of x is equal to, so whatever the maximum degree of the polynomial, you're going to call that n. So if n is 5, this is a fifth degree polynomial function. N is 215, and is, that's a 215 degree polynomial function, right? So the coefficient is going to be just some number, and we're going to call it a sub n. In other words, this means the coefficient belonging to this term over here. Okay. All right. So the next term in mustahab form, in mathematical manners form, is going to be one less than this if it exists, n minus 1, right? Because there could be missing terms too, right? Okay. Yeah. And then the coefficient belonging to this, we're just going to label this as a n minus 1. In other words, the coefficient belonging to this term. Plus the next term is going to be x to the n minus 2, and the coefficient, you can call it n minus 2. You're going to use a, you could use b, you could use c, but you're going to use one alphabet, because if you start using different alphabets, you're going to run out of alphabets pretty soon if you're dealing with polynomials, right? And this is going to go on all the way to the end, right? Until, let's say, x to the what? X to the first, right? This is going to be a to the first. And then the last term is going to be x to the 0, which is going to be gone. That's going to be the constant term. That's going to be a to the 0. It's x to the 0. And then x to the 0 is 1, right? So, like this. Okay? So, this is how you write a generic polynomial function. And the first thing that we should be able to do is you should be able to be comfortable writing this. So what I would request you to do is, if you're not comfortable writing this, just write this out until you are comfortable. That just writing this fancy schmancy lettering over here. So write this out, like, I don't know, 3 times or 5 times, whatever it takes, until you feel comfortable writing this. So it's actually very, very, very important that you feel comfortable with this term, what you see in front of your screen over there. Okay? So this is a generic polynomial function. This is a polynomial function. It's kind of like ax plus by equals c for all of polynomial functions. It's like a generic linear function. This is a generic polynomial functions. Okay? That's the first thing. There's 2 other things I wanted to talk about before I finish today, inshallah. Okay. Now, the second thing I wanted to talk about, how do polynomial functions look like? Okay? How do polynomial functions look like? Well, we know that if you have y equals 3x plus 2, this is a line. It's a polynomial function, right? Y equals x squared, that's a parabola, right? We know this, right? How about if we keep going like this? How about y equals x cubed? How about y equals x to the 4th? How about this? Y equals x to the 7th minus 6x to the 6th minus 4x squared, blah, 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 blah. How do they look like? So what can we generally say about polynomial functions? Okay, so polynomial functions, the best, easiest description of them is kind of like this. Okay, here, they do one of these. They kind of like, you know, swim around in the Cartesian plane. So if you want a generic polynomial, here I'll give you one. Here's a polynomial. Okay, so I'll tell you what's not a polynomial. Okay, this is not a polynomial because they don't have these sharp edges over here. Okay, that's not a polynomial. And this is not a polynomial. Okay, and this is not a polynomial. Okay, so these are some examples of what polynomials are not. So polynomials have smooth contours like this, and they kind of live on. Now understand that line is probably the only exception of polynomials are straight. Okay, other than that, they're curvy thingies. Okay, polynomial. There's some other terms that are important to know. So I'm just going to talk about some of these other terms of polynomials. So here's a generic polynomial, okay? Okay. So as you can see, the polynomial has some peculiar, it looks like, hills and valleys, right? Okay. So these are called turning points. Okay, as you can imagine, these are turning points. Okay, these are turning points. Here's a turning points. And you can call this, for example, local maximum. Right? And this is kind of like a local minimum. Local maximum minimum is because this is not the maximum value of the function, because the function over here, for example, is lower than this value right there, It's not the lowest the function would be, but it's like local. Within this area is the lowest. Within this area, that's the local maximum. So that's local maximum and local minimum. And you can call this one, is if this is the highest the function goes, like the absolute maximum of the function or something like that, Here's some terms. Here's local maximum and a turning point, global maximum, okay, or absolute maximum, global maximum, okay, and this is like a local minimum, okay. Here's enough. Polynomial functions always have smooth graphs with no discontinuities. That's actually very important. You have no discontinuities, okay. So this is you can call this a global or universal absolute maximum, global maximum. Okay. There's two other terms that I wanted to bring to your attention here. Okay. One is this. The x-intercepts end up being very important for polynomial functions. Okay. Like here, y-intercepts, who cares? But we do care. But x-intercept end up being very important for polynomial functions. Okay. And these are called. These x-intercepts, they're called. You can call them x-intercepts, for one thing, but they're generally called zeros of the functions. Okay. The zeros of the function, because for every x-intercept of y is like 0, right? Some x, okay, some x and 0. So when you say zeros of the function, we mean x-intercept. That's like the lingo, that's like the colloquial language for, so to speak, for polynomial function, because they actually become a very important aspect of, for example, graphing them and understanding the polynomial functions. Okay, so the x-intercepts are very important for polynomial functions. So the x-intercepts are called zeros of the function. Okay, and in this case I have 4. And one last thing, this is the last topic I'm going to talk about before I finish today, is something called end behavior. of a polynomial function. Okay. End behavior of a polynomial function is what the function does in the end over here. Okay, that's called the end behavior. Because a polynomial function cannot have infinite number of valleys and hills. Okay, it has a fixed number, and how many valleys and hills it's going to have depends on the degree of the function. Okay, so it's not infinite number of valleys and hills. It depends on the degree. So, but in the end, it's doing something. In this case, the end behavior is this is going down like this. Okay, that's called the end behavior. Now, what is the function doing as x approaches this infinity and x approaches that infinity? So I'm going to talk about the end behavior of polynomial functions here. Okay, so to understand this concept of end behavior, you have to appreciate, you kind of have to know like two polynomials, okay? To kind of keep it in mind, that it helps you a lot, okay? So the first one is y equals x squared. We're quite familiar with this, right? So this is a quadratic. This is a parent function of a quadratic function. And when we say end behavior, we mean, what does the function do as x goes to positive infinity, and what does the function do as x goes to negative infinity? Okay? So in this case, you can say the function f of x, what does it do? It goes where? As x goes to big over here, what does y do? Y gets very, very, very big, goes to infinity. So f of x goes to positive infinity. That's the symbol for infinity, positive infinity, okay, as x goes to positive infinity, right? Okay, so you can write this as this, or some people write like this, positive infinity, or something like positive infinity. It doesn't really matter. I mean, I think it's, both is okay. So f of x goes to positive infinity as x goes to positive infinity. And on this side, the end behavior on this side, what does the function do? F of x still goes to positive infinity, let me put it like this, as x goes to negative infinity. As x goes to negative infinity, the function goes to positive infinity. Okay? So the end behavior here of this function can be described as f of x, I mean, it is different color, okay? The end behavior of this function can be described as f of x, okay, goes to positive infinity as x goes to positive infinity, okay, and f of x goes to positive infinity as x goes to negative infinity, okay? So this is the end behavior of this function. Okay, so you have to kind of know the end behavior of this function like that. So if somebody asks you what's the end behavior of this function, you would say, okay, the function goes to positive infinity as x goes to positive infinity, and the function goes to positive infinity also as x goes to negative infinity. So this you have to understand, okay, because you have to memorize this, because you're going to use this and apply this to polynomial functions of all kinds. The second function that we have to remember in understanding end behavior is this function over here. This is f of x equals x cubed. Okay, now look at this. Let's describe the end behavior of this function. Okay, the end behavior of this function is this. F of x goes to, what is f of x? Goes to positive infinity, okay, as x goes to positive infinity, okay? Or you can say, you can also say this, as x goes to positive infinity, f of x goes to positive infinity. Okay, and as x goes to negative infinity, okay, f of x goes to, in this case, negative infinity. See, that's different from y equals x squared. In y equals x squared, as x went to positive infinity, f of x went to positive infinity. As x went to negative infinity, f of x went to negative infinity. Okay? Yeah, in a positive infinity for the other function. Got it? So now, these are very important because all polynomial functions are going to behave like this. Okay? In other words, okay, if you were to draw these two functions out over here, like this, okay, this is that y equals x, f of x equals x squared, and this is f of x equals x cubed. All polynomial functions are going to behave like this. In other words, look at this function. This is a polynomial function. And look at this function. These are two polynomial functions. Now this polynomial function's end behavior is the same as the end behavior of this polynomial function. And this polynomial function's end behavior is the same as this polynomial function. Do you understand? So you have to understand these two basic polynomials, y equals x squared and y equals x cubed, and model the behavior of the polynomial functions compared to this. Okay? And it's very easy. Okay? Any polynomial function that is even degree, like x to the fourth, okay, minus 5x cubed plus 2x minus 5, okay, any polynomial that's of even degree is going to behave like this, okay? And any polynomial function that is odd degree, for example, negative x to the 13th minus 4x to the 12th minus 3x plus 1, for example, of odd degree is going to behave like this, okay? Easy enough. So the end behavior of this function is going to mirror the end behavior of this. But one caveat, okay? If this a is positive, it's going to behave like this, okay? So the end behavior of this function is going to be modeled by, okay, y equals x squared. Now if I had this function over here, minus x to the fourth minus 5x cubed plus 2x minus 5, the end behavior of this function is going to be modeled by y equals negative x squared. It's going to look like this. Okay? Do you follow? Since this is also negative, the end behavior of this function is not going to be this. It's going to be f of x is going to be negative x cubed. Okay, that's important. So let me give you a couple of examples over here, okay? So, let's do this one. This is g of x is equal to minus 2x to the fourth minus x cubed, okay, plus 4x minus 5. Now we're going to describe the end behavior of this function. In other words, this function is going to like snake around in the Cartesian plane, right? It's going to be one of these. But the question is, what's the end behavior is going to be, okay? Now this function has even degree, so it's going to behave like f of x is going to equal to x squared, but it's negative, the coefficient is negative, so it's going to behave like this. So the end behavior of this function is going to be same as the end behavior of this function. So it's going to look like this. So which means whatever this function does in between, okay, in the end it's going to go this way, in the end it's going to go this way. In between it could be doing whatever it's doing, like this. Do you understand? So this is the end behavior of this function. Now how do we put that in, in mathematical language, right? So you say as x goes to positive infinity, f of x goes to negative infinity because it's behaving like this. And as x goes to negative infinity, over here on the left side, f of x is going to go to negative infinity. So this is the end behavior. This is the end behavior. Let me do it like this. Okay, of this function over here. Do you understand? So that's how you describe the end behavior. So that's important in graphing these functions. So and then all of them you have to figure out what's going on in the middle. Okay, so let me give you another example. How about this function? F of x is equal to 5x cubed plus 3x squared minus x plus 7. Let's talk about the end behavior of this function. Okay, now this function is odd degree, right? So that's odd. So that's going to behave like y equals x cubed. Okay, and since this is a positive 5, it's going to behave just like that. It's going to behave like this. The end behavior is going to be described by this. So the end behavior of this function over here, f of x, is going to be as x goes to positive infinity, f of x goes to positive infinity. And as x goes to negative infinity, f of x goes to negative infinity. Okay, so this is the end behavior of this function. Okay, so in summary, what did we learn? We learned what polynomial functions are, and we described a generic way of writing polynomial functions such as this. Okay, and a to the x plus a0, and then we learned about end behavior of polynomial functions. End behavior of polynomial functions, and we learned some basic terms such as local, maximum, and minimum, and turning points, and the very important x-intercept or zeros of the polynomial function. Inshallah, next time we shall explore some of these topics in more detail. Until then, as-salatu was-salamu ala rasulillah wa rahmatullahi wa barakatuh. Assalamu alaikum.